what I'll call B prime, which is the point B after we pull on it with that force P, it moves down by 0.2 millimeters. And the original length of the wire from C to D, which I'll call L naught, since that's what we're going to want to know the strain in, it's originally unstretched 300 millimeters. And we want to find the normal strain epsilon CD. We're not making a free body diagram in this. We're not looking for forces. We're just looking at the geometry. How can we figure out, if we know how far point B moved, how can we figure out how far point C moved? A similar triangle is what we're going to draw. So what we can draw is at point A, originally, our bar looks like this. It's 400 millimeters and 200 millimeters. Again, some artistic license here. When we deform it, the bar's length does not change. It just rotates down. Point B up here moves down to point what I'll call B prime, and we're told that that length is 0.2 millimeters. If this is point C and this is point C prime, right, it's delta. It's, if the wire was originally this long, we've added delta to it, is one way we could label this. So the wire is still connected up here, but now instead of being C down here, C or C prime is now here. So this represents how much longer does the wire get, since point D is stationary. So the equation we can use here to find delta, we can use similar triangles. Since this is a right angle, this is a right angle. We know that in similar triangles, the ratio of the legs are equal because they both share this angle, I'll call theta for right now. Which means that the ratio of this leg to 400 has to be the same as this leg to AC. Right, so again, for this one, I'm using triangle ABB prime. And for the right-hand side, I'm using triangle ACC prime. Because they share this angle, they share all the same angles, the right angle and this theta. Right, so you should get that prime, the new length of 3. To do that step, because remember we had two ways we could calculate the normal strain. Really, it's just a change in what we call the numerator. We can use delta over L naught, the change in length of the wire from unloaded to loaded, divided by its original length. We just found that it's, when we apply that force P, it stretches or changes its length by 0.3 millimeters. And its original length was 300 millimeters. Here I have consistent units of millimeters and millimeters. The normal strain in CD is going to be 1 times 10 to the negative third millimeters per millimeter.